Hello, class. Okay, so we're going to talk about a few new concepts today, work, energy, and power. And we're going to start out by defining work. Now, the most basic idea of work is you apply a force through some distance, then you're doing work. Like say you have an object and you're just pushing it along the ground. So you're applying a force through a displacement, and that means you're doing work on the object. But we're going to have to kind of build up our definition of work in pieces. And let's start out. Let's say we have an object. And we're going to apply a force. Let's say it goes through a displacement delta x. Now, we're going to start out by saying, let's say we apply a force in the direction of displacement. Let's call this case 1. In this case, the work is simply going to be the force times displacement. So here, force and displacement, let's say force is parallel to displacement. And so you simply multiply the two. Now, one thing, let's talk about units for a moment. Force is newtons, displacement is meters. This product, a newton times a meter, we give that a name, we call it a joule. A joule is equal to a newton times a meter. Now, this was named after someone named James Joule, who was a scientist like during the Industrial Revolution. I think he worked on like heat engines and things like that, but they named that unit after him. So a joule is a newton times a meter. So in this particular case, force and displacement are parallel. Work is simply force times delta x. Now let's consider case 2. So in all these cases, the displacement is going to be, say to the right. So for case 2, the force is to the left. And in that case, we say work is minus the force times the displacement. So here we have force is anti-parallel. To displacement. So they're along the same line. Displacement is to the right, force is to the left, but they're in opposite direction. So like if you have like line of force and a line for displacement, the lines are parallel, but because they have directions and they're opposite directions, we say that the force is anti-parallel to the displacement. Okay, and we're going to consider one more case. Okay, case 3. Where force is perpendicular to displacement. And in that case, the work is 0. Now, what we've been doing here is finding the work done by individual forces. So, for a practical example, we could have multiple forces acting on this object. Like, let's say we're applying a force. We're pushing this object. So it's going to move in that direction. Maybe there's friction acting on the object. There's gravity acting on it. And so, yeah, we can calculate the work due to each of these forces individually. So like the work done by the applied force would be F delta X. The work done by friction would be the friction, or minus the friction force times the displacement. The work done by the normal force is 0, and the work done by gravity is also 0 because they're perpendicular. And these are the only three cases we need to consider. Now, the most general case that we're going to consider, forces don't always have to be either parallel or perpendicular to the displacement. So let's look at one more case, but I said, we're only going to consider these three cases because that's all we actually need. But let's look at how we would handle, a more general case where we have, say we're pulling an object across the ground with a rope. So imagine you have like a sled or something or a cart, and you tie a rope to it, and the rope's over your shoulder. So, the rope makes an angle with the sled. So I'd say we have a force applied in this direction, and the displacement is going to be just horizontal. So clearly this isn't any of these three cases, except we can calculate the work done by this force fairly easily by just breaking the force into components. We can always break it up into components where one is parallel to the displacement. Let's call that F parallel. And the other component would be perpendicular. And basically what we're saying is, we treat this force as two separate forces. And, so the work due to this force would be the work due to F parallel. Times the displacement. Plus the work due to this perpendicular component, which is 0. So the total work is just F parallel times delta X. And usually we define this angle, theta, to be the angle between the force and the displacement. And so you can write it like this as well. So like the component of force in the direction of displacement is F cosine theta. So we have F cosine theta times delta X. Usually we just put the cosine theta at the end. So this is our most general definition of work. Now, there are important cases though where this doesn't really work because, what if the force is not constant? What if you're pushing an object and the further along you go, the harder you push it? So when the force is changing, basically what you do is you'd still use this formula, but you'd have to break it up into small displacements where the force can be considered, it doesn't change much over a small displacement. And for the most general result, we'd get into calculus, where we could have an exact definition of work done by a variable force. So we're not going to consider those. Okay. So basically we've defined force. And remember, force is basically, you think like a force times a displacement. But you have to remember forces and displacements are both vectors, and so we have to take direction into account. So that's our basic definition of work. Now, what good is this? We're going to look at an important example. Now, for our purposes, we're going to have to consider a special case here. However, the result we're going to derive applies more generally than what we're considering here. But let's say that we have an object that is acted on by constant forces. And to make things easier, let's say that the net force is in the direction of the displacement. So we're going to consider like a one-dimensional problem, where this object is moving, say, in the x direction. It's going to go through some displacement in the x direction. And let's say the net force is in that direction. Now, again, we're just doing this to make things easier, but there's a more general result where you can consider, any displacement, and the force can be non-constant as well, and the result is the same. So we're just going to show that this is true for a special case of one-dimensional motion with constant forces acting on this object. And so we have this mass here, and we can write down the net force here. And we want to talk about the net work done on an object. Now the net work, we could define that in two different ways, or we could calculate that in two different ways. One way, let's say we have like three forces acting on an object. Say F1, F2, and F3. And we can calculate the work due to each of those forces individually and add it up. So we can say the net work would be W1 plus W2 plus W3. Now another way you could calculate the net work would be to just take the net force, and then you have a single force, then you just apply this definition. So either way, you can calculate them individually, or you get the same result either way. So let's say that we have, the net work in this case is going to be simply F net times delta x, because they are parallel to each other. So we're just considering an easy example. Now, the net force, so again, we have to calculate the net work, because the net force is equal to mass times acceleration. Now let's say our displacement is going to take us, say, from point A to point B. So we're going through this displacement from point A to point B. And let's say we started with a speed VA, and we're going to end up with a speed VB. So like in this case, if the force is in the direction of displacement, VB is going to be greater than VA. We're accelerating and speeding up. And because we're considering constant forces, we know that the acceleration is constant. So if you go back to Chapter 2 Kinematics, in this case we can say VB squared equals VA squared plus 2A delta x. So our displacement is delta x. Remember, like the velocity at the end squared would be the initial velocity squared plus 2A delta x. And we can rearrange this. If you look here, we have A delta x. Here we have an A delta x. It's not exactly by itself. So let's rearrange things a little bit. We can say 2A delta x is equal to VB squared minus VA squared. And then if we divide by 2, we have A delta x by itself. So let's do that here. A delta x, we just have a 1/2 in front, so let's write it here. And then we'd have VB squared minus VA squared. And we can write this, if we expand this, we can say 1/2 m VB squared minus 1/2 m VA squared. And so by calculating the net work on an object, we get these terms 1/2 mv squared, for the two different points, A and B. And what we're going to do is we're going to give that a name, and we call that kinetic energy. So we define the kinetic energy of an object to be 1/2 mv squared. And then the result here, we can just write this in a much simpler form. We can say work net. Here we'd have the kinetic energy at the end of the motion, that would be KB, minus the kinetic energy we started with. And so this is called the work energy theorem, where the net work done on an object is equal to its change in kinetic energy. So first we had to define kinetic energy. We say it's 1/2 mv squared. And if you just look at that formula by itself, you might be a little confused, like why would we define it that way with a 1/2 in front of it? But now we can see that that's a sensible way to define it, because these kind of terms show up when we do these calculations. So it's a very useful definition. And again, we showed this for a case of one-dimensional motion with constant forces. But the result is true in general. So you can have variable forces and motion in any 2 or 3 dimensions, whatever. Work energy theorem is just true in classical mechanics overall. So that's a very important result. All right, I think I want to talk about just one more thing. I want to make sure I'm not forgetting anything. Yeah, one more thing we're going to talk about, and that is power. So let's look at a quick example. Let's say we have a mass. Let's say a mass of 62 kilograms. Just made that up. And let's say we're going to lift that up. So we say I have a rope, and we just lift it up through a height h. Now let's say we're going to lift this at a constant speed. That's the easiest way to lift it, or at least in terms of the most efficient way to do it. So we lift this up with a constant speed. So let's just say we look at some point. We have tension up and gravity down. Let's calculate the work done by, say, tension. Height. Let's lift at a height of 4 meters. So we lift it vertically up 4 meters. Now the work done by tension would just be the tension times the height. Let's actually work this out here. The work done by tension would just be tension times the height. So force times the distance in this case, because we're lifting it up and tension and the displacement are parallel. So it's a positive value here. So work is tension times height. And because we're lifting this object at a constant speed, we know that the tension has to be equal to mg. Tension has to be equal to the weight, so there is no net force. So this would be mgh. Now this result is true in general. It doesn't matter if the tension is equal to the weight or not. The work done by tension force is always going to be T times H, if they're both in the same direction. But because we know it's moving at a constant speed, we can replace tension with mg. So let's do that. Okay, 9.8 times 4, just cheat and use a calculator. So we have 62 times 9.8 times 4. Now mg, that would give us a force in newtons, height in meters. So yeah, we'll get joules out of this. This will be around 2,430 joules. Now we can also calculate the work done by gravity. Now, the work done by gravity, because the displacement is up and the force of gravity is down, we have a minus sign in front. However, the magnitude here is the same. Because we're lifting at a constant speed, so the net force is 0. So the work done by gravity is minus 2,430 joules. And then the net work done is 0. So if we're lifting at a constant speed, then the acceleration is 0, the net work is 0, or the net force is 0, so the net work is 0. So again, in that case, tension and gravity have the same magnitude, just opposite directions. Okay, now, we're going to find something new, but let's look at a different example now. Let's say we lift this at a non-constant speed. So let's say we apply a tension of, say, 3,000 joules. So in that case, tension is no longer equal to weight. So in this case, the value here we'd have I should probably give a force instead. Yeah, let's just do 62 times 9 point. Let me erase this number. Let's calculate that. But the weight is around 620 newtons. Let's say we apply a force of 800 newtons. So here, work would be tension times the height. So if we have 800 newtons times 4 meters, that would be 3,200 joules. And so now the net work in this case would just be this difference. So 3,200 minus 2,430, let's see. Yeah, 770 joules. So yeah, we've done net work in this case. And the result of that is that there's going to be a change in speed. Like say that we started out at rest, how fast is this object going to be moving after it's gone through this displacement of 4 meters? Well, we know that 770 joules is equal to the change in kinetic energy. So that'd be 1/2 mv final squared minus 1/2 mv initial squared. Let's say it started out at rest. So we can calculate the final velocity by, let's multiply this by 2, divide by the mass, and take the square root. So if we multiply that by 2, that's 1,540 joules. Divided by the mass, which was 62 kilograms. Now a joule is a newton times a meter. So we have a kilogram meter per second squared. That's a newton. And then we multiply it by a meter. So if you break it down to the basic SI units, a joule is a kilogram meter squared per second squared. So if we take a joule and divide by a kilogram, we have meters squared per second squared, and then we take the square root, we get meters per second. So let's do this. 1540 divided by 62. That's 2.48. So yeah, the final velocity would be 1.58 meters per second. So we can calculate that using the work energy theorem. Another way to calculate that would be to find the acceleration, which would be the net force divided by the mass. So the net force would be 800 minus mg, 62 times 9.8. We could find the net force, divide by the mass to get the acceleration, and then use this equation. If we assume we started out at rest, we'd have v squared equals v naught squared, that's 0, plus 2a times the displacement, which was h. And so, we should get the exact same number if we do it that way as well. Why don't we do it? I said the exact same number, but there will be a little rounding error. But let's find the, we'll do it this way as well. So the net force, let's look at the weight, 62 times 9.8, that's 607.6. So the net force, like a little room here, that's 192.4 newtons. So the acceleration, we divide that by 62 kilograms. We have an acceleration of 3.1 meters per second squared. And then the final velocity squared would be 2 times the acceleration times the height. So if we take that acceleration, multiply it by 2, and then multiply it by the height, getting that would be meters squared per second squared. So acceleration is meters per second squared times the height, which is in meters. And so let's take the square root. Wait, these numbers are not checking out. Let me double check that. That looks good. That number looks good. I'm going to have to recheck this number. But let me see. Yeah, I don't know what I did there. I'm sorry, I'm glad we checked this because this number is wrong. So let's recalculate that one in a moment. But here we have 24.8 for v squared. If we take the square root of that, we get around 5 meters per second, like 5.0 meters per second. Now, let's go back here. This part was right. But if I divide this, let's do that. 1540 divided by 62. Yeah, 24.84. And then take the square root of that. Yeah, we get 5.0 again. So I have no idea what I did earlier in just going from here to here. I made some mistake, but you can see we get the same result using just kinematics, like net force and kinematics, or the work energy theorem. But like I said, I wanted to kind of talk about this last concept of power. Like we do a certain amount of work to lift up this mass. Like in this example, we did say 3,200 joules of work on this mass to lift it up that 4 meters. Now, the work that we do, it doesn't matter if we did that work in 1 second or 1 hour. The work is the same. It only depends on the force and displacement and not on how long it takes. So to take time into account, we define power as just work over time. And power, work is measured in joules. Time is measured in seconds. We give that a name. We measure power in something called watts. That was named after another scientist from the Industrial Revolution. I think it was James Watt, and so we named this unit after him. So a watt is equal to a joule per second. So again, power is just a measure of how quickly you're doing work. Okay, so basically this lecture, we just defined some of the basic things like work, power, and kinetic energy. And then we're going to have another lecture where we talk about another form of energy called potential energy, but that'll be a separate video. I think we'll stop this one here.